first example of determining the rate law, and here's the question. If you have A plus 2B, this yields the product of 2C, so that's your the reaction, and you can see that there's it's a balance, or sort of a balanced reaction if you have A and B giving you C. This is the experimental data. That means that it's usually in a table form, so this is going to be your trial 1, trial 2, trial 3. This is the amount of the concentration of A that you started off with, and this is the amount of B that you started off with. And this is looking at the rate of decomposition. That means that when this and this were to combine together, this is the amount that it will sort of decompose to make C. And this is all individual trials. So what you want to do is that when you want to figure out the rate law, this is your basic sort of reaction, right? So if we were to just looking for for A, this is rate is equal to K is with the multiplied by the concentration A to the power of X, right? So if we wanted to look for this one, well, your rate law is going to also include your second concentration because B is also involved, and we'll just use Y as the other order. So how you want to do this is that basically you want to look for each of these concentrations by itself first. And what you're doing, or what we're doing in this math, is just looking at the ratios and comparing the two different trials to get really the order of the reaction. So the key here right now is really looking for the X and the Y's, the exponents, or the order of the reaction. So let's look at this. In order to determine this, we need to find two trials where the concentration of one stays constant while the other one will be changing. And you can see that if we were to select trials 1 and trials 2, for trials 1 and 2, A is actually increasing while B is staying the same. This makes it a lot easier for calculations. So if you look at this, we're comparing the ratio. So if we have the rate of trial 2 divided by the rate of trial 1, then we can ignore the K for this calculations, but because it doesn't really matter yet, and we can look at the concentration of A divided by concentration of A in trial 2 and trial 1. And remember, they all both have an exponent of X because that's my order. So this is my order, that's my X. You can actually incorporate concentration of B in here, and I'll show you the reason why we want to keep one constant, because if we were to keep one constant, this just basically cancels out. So let's look at this. What's the rate of trial 2? It's 1.5 divided by 0.5. This is equal to concentration of A in trial 2, so that's this one. That's 3.0 divided by trial 1, which is 1.0, so that's 1.0. And then this is to the power of order. And if we wanted to incorporate the concentration of B, you're going to see that this is actually just going to be 1 and 1. So this is just 1 divided by 1. I don't know why I put another bracket there. I don't really need to. And because they're just 1 divided by 1, this will just cancel. So that's the reason why you want to find one where the other one stays constant. And after this, you just have to do the math. So 1.5 divided by 0.5 is just 3 times, so that's 3.0 is equal to, so now this is 3.0 or 3 divided by 1 to the power of order, and we try to figure out what the order is. So let's do what's inside the brackets first. 3 divided by 1 is 3, and we still have the exponent of order. So now you have to ask yourself, what must this exponent be to equal to 1 or to 3, right? So you're going to see that 3 has to have, the order has to have the power of 1, because 3 to the power of 1 will give you 3. So the order for A is 1. So we just solve for that. If we wanted to solve for concentration B, we do exactly the same steps. So let me just kind of scroll down here. And so for concentration B, again, this is my rate is equal to K, A, and now we have the order 1, we can put a 1 here, and then B is still Y. So then we have to go back in our initial rates, in our table data, and find two trials where A is going to keep constant while B will move. And you can see that very easily that in trials 2 and 3, A is staying the constant while B is changing. So we need these numbers. So what's my rate? I have 3.0 divided by 1.5. So my rate is 3.0 divided by 1.5. So again, this is from trial 3 and this is from trial 2. I think that's right. Yeah. And then you're going to see that for concentration B, trial 2 has 1 and trial 3 has 2. So I'm going to include those. So you can see that this is equal to, we ignore the K here. So we don't need the A because we kept that as constant. It was just equal to 1. For B is, I totally just lost, I forgot what it was. I think it's 2 and 1. That's right, it's 2 and 1. So this is going to be 2.0, 1.0, and this is all to the power of the order. That's what we're trying to find. So we'll just do some math here. 3.0 divided by 1.5 is 2, is equal to 2.0 to the power of order. And you're going to see that in order for this right side to equal to the left side, the order must be 1. That's it. And once we solve for the order, we can finalize our equation. So rate law is equal to K. A has an order of 1, B has an order of 1. So why is this useful? Because now we can actually determine what our rate constant is by subbing the numbers in. So if I wanted to calculate for the rate constant, I can use any of these 3 trials, sub in the numbers, and solve for K, and that's it. So that's the first example. Let's look at a more complicated example in question 2. This one is you have your iodine, you're reacting this with oxygen and chloride here, and you can see that this is your trial table, your initial rate. So this is the concentration of your iodine ion, and you have your ion of the other one, and this is the rate of sort of consumption. So you're calculating for the rate law. So the first thing is I'm just going to write the rate is equal to K is equal to I minus OCl minus, and I have my X and Y. So first is determine the rate law. So again, I'm just going to go through these 4 trials and find 2 trials where one is going to be kept constant. And you can see that this one, trials 1 and 2, OCl minus ion is constant while the other one is changing. So I'm going to use that. So I'm going to go rate of trials 2 divided by rate of trial 1 is equal to concentration I ion divided by I ion of 2 and 1. So this is going to be to the power of order, which is your X. Sub in some numbers, so I'm going to put this number in here. So this is going to be 3.95 times 10 to the negative 2 divided by 7.1 times that is equal to 0.060.12, and then this is all to the power of the order. So then I'm going to punch this in the calculator, 3.95 to the power of 2 minus divided by 7.9. This is 0.5 is equal to also 0.5 to the power of order, and you can see that the order here is going to be 1. One, I guess, tip here is that I selected the lower one divided by higher one. So you have to sort of notice that I use trials 2 divided by trials 1. I don't always have to use the higher trial divided by lower trial. What I want to do to make my calculations easier is actually use the bigger number divided by the smaller number, because then you just get a whole number. Otherwise you have this decimal number, which sometimes could be difficult to determine the order. So that's the order of my iodine ion. So let's look at the other one. So for my OCl ion, now I need to look for 2 trials where the iodine ion is kept constant while the other one is changing. So let's look at these. You can see that this is 0.12. Okay, so I have 0.060 and 0.060. So I'm going to use this one because then I don't have to incorporate iodine ion in my calculation, because it'll keep constant, while this one, OCl minus ion, will be changing. So then am I going to use the 4th trial divided by the 2nd trial, or the 2nd trial divided by the 4th trial? So I'm going to use, I'm going to use the bigger number, 0.18, divided by that one, so then I'll get a whole number. So let's try this. So the rate, I'm going to use trials 2 divided by trial 4 is equal to, this is going to be my OCL minus, divided by OCL minus, oh, the writing is not very nice, and this is going to be from trials 2 divided by 4, extend the page. So my concentration for number 2 is, let's see what it is. So it's going to be 0.18 divided by 0.09. So this is going to be, the screen is moving all over. 0.18 divided by 0.09. This is all to the power of the order. And my rate here is for rate number 2 and 4. So the rate number 2 is 3.95 times 10 to the negative 2. And then my trial 4, the rate is 1.98 times 10 to the negative 2. So divide by 1.98 times 10 to the negative 2. And then do the math, you can sort of see that this is going to give you 2. And then this is also going to be 2 to the power of order. And now the order is going to be 1, right? Because 2 to the power of 1 is going to give you 2, so 2 is equal to 2. So then you just solve for the ion OCl minus with the order of 1. So once you have the order, then you can calculate your rate constant by just subbing it in. So remember, your rate law is now going to be K, this is your iodine ion, has an order of 1, that's what we just determined, and then also OCl minus ion has an order of 1. So then we can calculate K with any of these trials. I'll just use the first trial. My rate for the first trial is 7.91 times 10 to the negative 2 is equal to K, that's what we're trying to solve. And then the concentration of I ion for this one is 0.12 times the concentration of OCl minus, which is 0.18, so 0.18, and then just solve for K. So multiply these numbers together, that's going to be 0.12 times 0.18. That gives me K multiplied by 0.0216 is equal to the same rate. And then isolating K will give me a final answer of, let's see, to the power of minus 2 divided by 0.0216. So my rate constant is 3.66, and there are no units for my constant. Oops, I totally just went right through it. So 3.66, and that's my rate constant. So once you calculate the rate order with all the exponents and all that, you can calculate for the rate law, or sometimes you can even calculate the rate if you're given the concentration, right? So if I were to give you like 5 molar here, 10 molar here, I can use that now to calculate the rate of reaction from my rate law. So again, rate law, the importance of this is that it quantifies it, and it allows you to determine exactly how much that you have. So those are 2 example questions of the rate law. Hopefully that has helped you. So see you next time.